So just to quickly review some of the things we did with probability. Remember, the notation that we used for the probability was this capital letter P, and then we put the event that we were concerned about in the parentheses there. So again, this P stands for probability, and this A means we're interested in the probability of event A. And then recall that probability only makes sense in the context of some sort of random event or process that's going on. And here we see those two different things that we need to concern ourselves with a random process. So A is, in order to event A to happen, sorry, if event A happens, it only makes sense in the context of some kind of random or uncertain outcome that would cause event A. And if you recall, this type of random process we called an experiment. So whenever we use that term in statistics or probability, that's what we're meaning is, what is that process that generates random outcomes? For example, like what's the weather tomorrow? Cloudy, sunny, rainy. Or if we roll a die, that's the experiment, because it could be 1, 2, 3, 4, 5, or 6, or flip a coin, or in the X-rail examples I gave, like how long are you going to live? That's the experiment. Then the second piece then is, once we know what experiment we're talking about or the random process, we need to concern ourselves with what all possible outcomes of the random process are in order to help us capture probability appropriately. And so that was what we called sample space. And that's what the text refers to as sample space. So it's the listing of all those possible outcomes of a random process. And it is important for it to be a good sample space. It has to really have all the possible outcomes, because we want the probability of something occurring to be 100%. And that will only occur if we actually identify the sample space in its entirety and make sure that every possible outcome will be represented there. So now when we think about how we have get a numerical value of a probability of an event occurring, well, sometimes, in fact, we might just be given it, or we might try and estimate it from just observing data. And sometimes that's the only way to get the probability of something. So, that in that kind of situation, we would just say probability of A is 0.6. 60% is the likelihood that this event is going to happen. If we repeat the random process over and over and over, we'd expect it to occur 60% of the times. Sometimes, though, when the random process has outcomes that can be easily counted, again, this is where counting comes in, the counting principles that we learned come into play. That's when we can actually compute some probabilities by actually counting things. And the way we did that was we had a fraction. The numerator of that fraction would be the number of elements in set A. So if we're thinking about an event, we want to count up how many outcomes are actually included in the event, and then we divide that by essentially the total outcomes. And I'll call that the number of elements in S, which is the sample space. And then that would give us a simple fraction. So like as an example, when we talked about rolling a 1 on a die, there's 6 sides. So our possible sample space would be 6 outcomes, and then rolling a 1 would be 1. And so the probability of rolling a 1 on a die would be 1/6. And so this notion here gets used quite a bit in probability situations, where we're basically trying to, in order to come up with the probability of the event, we're going to count up the number of elements that are in the event divided by the total possible number of elements. And one really important thing we talked about in class was that this counting process only works when the elements in the sample space, so all the outcomes, are equally likely. Yeah, so the idea here is that the only way this probability fraction works is if when you count up all the possible outcomes, each outcome in that sample space has an equal chance of occurring. The example we saw in class was when you sum the 2 dice, the outcomes of the sum were 2 through 12, but those elements were not equally likely. So you can go ahead and review that concept from the prior lesson if this still is not clear to you. And then really the last thing we covered in our last lesson was this idea that of the probability of 2 events one event or another event occurring. And the way we wrote that is the probability of A or B occurring. And so now here we've been dealing with a single event. Here we're thinking about the probability of one event or another one occurring. This should feel very similar to our set theory that we learned. And in this case, we actually couldn't write this as the same thing as the union. So the probability of two things, one or the other occurring, is the probability of the union occurring, one or the other, or possibly both. And so we can go ahead and write that. And then this, thinking of probability this way, allowed us to think about using the inclusion-exclusion principle. So in order to get the probability of one thing or another occurring, we're going to go ahead and add those probabilities. But just like when we counted unions, we have to worry about this possibility of the overlap. And here, in order for this probability of one thing or another occurring, we have to make sure to subtract out the overlap. And again, if you don't want to memorize the formula, you can always just kind of remember this Venn diagram picture. And if we have A and B, if we want to know the probability of being anywhere inside these circles, we have to add up the probability of being in this circle plus the probability of being in this circle, but we're double counting this little piece here, and that's why we have to go ahead and subtract. So this gives us the probability of one event or another event occurring. And then we also had the special situation where A and B are mutually exclusive, and this actually allows it to simplify it. And just to remember again what mutually exclusive means, that means essentially means there's no overlap. It would be a picture like this. We have A and we have B. You know, as an example, if you roll a die, A could be the outcome of even number, B would be the outcome of odd number, and in that case we would say A and B are mutually exclusive because if one occurs, the other one can't occur. And so all that really is going to mean here is that intersection is in fact 0. And so if they're mutually exclusive, we can go ahead and simplify this, and this turns out to be the addition principle, but in the form of probability, where the probability of A or B occurring is just we get to add them up. And we don't have to worry about subtracting the overlap if they're mutually exclusive. So it's going to go ahead and finish writing that. So if they're mutually, sorry about the spelling there, mutually exclusive, then we get this more simple case of just being able to add the probabilities. And we're actually going to end up using that quite a bit. But just remember, this only works if A and B are mutually exclusive. If they're not, you need to worry about subtracting off that overlap.